Hey everyone, welcome back to Math with Vanch. I'm Vanch and I will be teaching you math, obviously. So in the last video, we finished Unit 1 with infinite limits and also limits at infinity. In this video, we will officially be starting Unit 2 with the definition of the derivative. So if you're ready, I am too. Let's get started. Okay, so first of all, what even is a derivative? So a derivative is literally just slope. So now if you remember in Algebra 1, we found slope using the slope formula, right? So the slope formula was m equals y2 minus y1 over x2 minus x1. Okay, and we can use this if we have like some type of function. So I'll just make up a random function right there, right? So something like that. And we would use this when we had 2 points. So suppose we had the point right here and the point right here. And we would use this formula to find the slope between these 2 points. So we would draw a line like that, and this formula would give us the slope of whatever this line is, right? And this would be if this is the point x1, and this is the point, x1, y1, and this is the point x2, y2. Okay, so this is when we would use that formula. Now the difference is with the derivative, we don't have 2 points, we only have 1 point, right? So if we wanted to find the derivative of this graph at 1 point, it's basically finding the slope, but just at 1 point. So this right here is a secant line, okay? We call this a secant line, and we use this slope formula to find the slope of the secant line. But we use the derivative if we wanted to find the slope of a tangent line. So a tangent line, so suppose we wanted to find, I'll redraw this graph. Suppose we wanted to find the derivative of this graph at this point right here. So first what we do, we draw a tangent line to the graph at this point. So a tangent line is where the line only intersects the graph at 1 point. So that would be right here. Something like that, right? And now the derivative of this graph at this point would be the slope of this tangent line. So that's kind of the difference between a derivative and the slope that we've been using since Algebra 1. And this is the formula that we've been using. And since we don't have 2 points here, we only have 1 point, right? We can't use this formula because this formula only works if you have 2 points. So for this, we have to do something different. And let's get into that now. So again, we want to find the derivative at this point, right? So let's kind of work our way there. So let's start off. So first of all, let's say that this function is f of x, right? And this point right here is x. Good. So then this point right here, this y value right here, this y value right here would be f of x. Okay, so then that would make this point x comma f of x. Now let's take another point right here. And we'll say that this point right here is the point x plus h. So x plus h. And we're saying that because this distance between the 2 points is going to be h, okay? So now we have 2 points where the x values are h distance away from each other. So the first point is at x coordinate x, and the second point is at x coordinate x plus h, okay? That would make the y value of this coordinate f of x plus h, okay? So now we have this point, which would be x plus h, comma, f of x plus h. Okay, and that's just the function, because if we have the function f of x, if we have x as the coordinate, x as the x value, then our y value would be f of x. And same thing if we have x plus h as our x value, then we would have f of x plus h as our y value, right? So now we have these 2 points. So now what we can do, we can plug these 2 points into this equation right here. So if we do that, we get our y2, which is f of x plus h. So f of x plus h minus f of x, which is our y1, minus f of x over our x2, which is x plus h, minus our x1, which is just x. Now if you can see in the denominator, we just have x minus x. So now we can just substitute, we can just cross out these x's, and we'll be left with h in the denominator. So all over h. Okay? So now this would be kind of our arbitrary slope between these 2 points. Now what if we made this distance h even smaller, right? Then we would have a better approximation of our slope of our tangent line. Okay? So the best approximation of our tangent line would obviously be when this distance is 0, because that would be our tangent line. That would be the slope that we want. It wouldn't be the slope between 2 points or 2 really close points. It would be the slope at the exact point. So to do that, we just have to set h equal to 0. But we can't do that because otherwise we would have 0 in the denominator. So we would be dividing by 0. So instead of setting h to 0, we would just do the limit as h approaches 0. So let me erase this. And we'll write the limit as h approaches 0. And that would make it so that this distance is 0. So these 2 points are like, well, it approaches 0, so it's not exactly 0, but it gets infinitely close to 0. So as this gets infinitely close to 0, these points get even closer together. This point is going to get even closer to this point right here. And that's going to make these 2 values almost the same, which is going to give us the slope of our tangent line. Because if we have the slope equation, if we have 2 really close points, like infinitely close points, then that's just going to give us the slope of the tangent line at this point. So once again, let's get that equation that we got earlier. We have y2, which is f of x plus h minus f of x, and then all over x2, which is x plus h, minus x1, which is x. And then again, we can just erase this and erase this because those 2 cancel out. So now we have f of x plus h minus f of x all over h as for the limit as h approaches 0. And this right here is the equation for a derivative for any f of x, okay? And again, this works because as h approaches 0, these 2 points get closer and closer to each other. So the line between these 2 points slowly becomes the tangent line that we want right here. So instead of the tangent line being right here, like that, it's slowly going to become closer and closer to that tangent line right there. So, okay, let's start off with some examples for this. Okay, so here we have the function x squared, right? And what if we want to find the derivative when x equals 0? X equals 2. So what do we do then? So that means that we want to find the slope of the tangent line of the curve when x is 2. So this point right here, and I've drawn the tangent line to the curve at that point, right? So we have this equation right here, the limit as h approaches 0 of f of x plus h minus f of x all over h, okay? So what we do, so we know that we want the derivative when x equals 2. So x equals 2. So we can take this equation and we can plug in 2 wherever we see x, right? So the limit as x approaches 0, I mean not x, h, the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, okay? And we know what f of x is. F of x is x squared. So wherever we see this f, we can just replace that with squared. So we can make that into the limit as h approaches 0 of 2 plus h squared minus 2 squared all over h. Okay? Now we can simplify this. So we can expand this 2 plus h squared into, if we just FOIL, we'll get, so 2 squared plus 4h plus h squared. Okay? And then minus 2 squared, which is just 4, all over h. Now we can see that this 4 and 4 cancel out. So now we're left with the limit as h approaches 0 of 4h plus h squared over h. And here you see that we can factor out this h in the top, right? So here we can make this into h over 4 plus h over h, and then this and this cancel out. So now we're left with, I'll rewrite this over here. So now we're left with the limit as h approaches 0 of this right here, of 4 plus h. Now we can just directly substitute this. And the reason we couldn't do this before is because if we directly substitute this, like say here, we have h in the denominator, which is 0, while we're approaching 0. And we can't directly substitute that because we can't divide by 0 in the denominator. So anyways, so now here we can directly substitute because there's no denominator, and if we directly substitute, h just equals 0, and we're just left with 4. So the derivative of x squared at x equals 2 is 4. So what does that mean? That means that the slope of this tangent line right here is going to be 4. Now we can also do this just regularly. We don't have to have this x equals 2 specified. So we can also do we can also just do it with the function, right? Kind of, yeah. So if we have the limit as h approaches 0, and we have the function f of x, so we have f of x plus h minus f of x over h, right? This is just rewriting here. And we know that our f is going to be x squared. So we can substitute that right here. So the limit as h approaches 0, so x plus h squared minus x squared all over h. This translates to, if we simplify this, we get the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. This x squared and minus x squared cancel out. So then we're left with the limit as h approaches 0 of 2xh plus h squared over h. Now again, same thing, you can see we can factor out this h from the numerator, and then we can cancel it out. So here, this is the same thing as h times 2x plus h over h. And then we can cancel this out. And then over here, I'll take this up here again. We're left with the limit as h approaches 0 of 2x plus h. And again, we can just directly substitute right here. So this h is just going to become 0, and that becomes 2x. So now if we wanted to say what is the derivative of the entire function x squared, we would say the derivative of x squared is 2x. And if you remember, when we did the same thing with x equals 2, we got the derivative of x squared at x equals 2 to be 4, right? So at x equals 2, derivative is 4. Now, we could do the same thing, but we can just plug into here for x. Because here we found a general solution for the entire function, or the entire derivative of the x squared function. So the derivative of the x squared function is 2x. And if we just plug in x over here, we get 2 times 2, which is 4. And that is also the answer that we got previously. So that is the formal definition of a derivative. I promise it gets easier. You don't always have to do all this work to find the derivative, but this is just kind of the definition and how it was first founded. So that was the formal definition of a derivative. And I know that was a lot of work, but there are way easier ways to find the derivative, and this was just kind of the hard way and how it was first founded. I will be teaching you the easier ways in later videos, I promise. But otherwise, that is going to be all for this video, and as always, if you have any feedback, please let me know in the comments so I can make my content better. Otherwise, I'll see you for the next video. Bye bye.